phase diagrams. So a phase diagram is a diagram or a map of the state or phase of a substance as a function of pressure and temperature. So pressure's on the y-axis, temperature's on the x-axis. And there are regions in this diagram that represent where that particular state is stable. And there are lines that separate the regions which show where the substance is in equilibrium between the two states. So there's a vaporization curve, a sublimation curve, and a fusion curve. And there's a triple point, which is a unique set of conditions at which all three states are stable and in equilibrium. That's T-butyl alcohol. There it starts to boil. So he's pulling a vacuum on it and lowering the pressure, and that causes the alcohol to boil. And then it stops boiling. 2 minutes later, it takes a while to drop the pressure. Do you see that? It's freezing. And it's boiling. That's the triple point. Freezing and boiling at the same time. You have solid, liquid, and gas all in there together. Is that crazy or what? This is crazy. I don't know what's the rest of the video about? So now it's all frozen. Any questions? Yeah. Is that cold or hot? I'd have to look at the heating curve of that to see. My guess is it might be So let's look at a phase diagram. So this is a phase diagram for water. So we have pressure measured in torr on the y-axis, and this is not to scale, so you don't want to use this to do anything precise. And on the x-axis, we have temperature increasing, also not to scale. So this is 760 torr, which is normal atmospheric pressure. And here we've got 0 degrees Celsius. And so where 0 degrees Celsius and 760 torr intersect, we see that we're on that line that's known as the fusion curve, because that's where the water is in the transition between liquid and solid. If you're coming from colder to warmer, it'll be melting. If you were warmer and you're coming, decreasing the temperature, then it'll be freezing. If we look at one atmosphere up at 100 degrees Celsius, we see that we're on the vaporization curve between liquid and gas. And this is the triple point for water. So a little bit above the freezing point, but at a significantly lower pressure. And then this is the critical point that we saw last week. Above this temperature, the liquid does not exist. It becomes a supercritical fluid. So that's called the critical point. And this is called the triple point. So we should be able to answer some basic questions by looking at a phase diagram. So we can look at changes in temperature by moving horizontally across the diagram. So here, going from negative 25 degrees up to 125 degrees, we see that here it's a solid. At this point, it's going to melt, and then it's going to become a liquid, and here it's going to boil and then become a gas. Or we can look at how the pressure changes. So we can say, well, here's regular atmospheric pressure. What happens if we lower the pressure at the same temperature? Well, lower the pressure, lower the pressure. At some point, the liquid will begin to turn into a gas. It will actually boil at room temperature. And as you continue to decrease the pressure, you will only have gas. So these are two other substances. This is iodine and this is carbon dioxide. And this is saying note the positive slope of the fusion curve. So the fusion curve is here. So that one has a positive slope, and this one has a positive slope. If we go back and look at water, water has a negative slope. That's weird. It's one of the many weird things about water. So what that means is that if you, say, are ice skating, and the ice obviously is going to be below the freezing point of water, it's frozen, right? And it's at atmospheric pressure, but you've got your ice skates on. And the ice skate has it has a blade, but it's actually curved so that it's a very thin edge on the inside and the outside. So very small surface area holding all of your mass. That puts a lot of pressure on the ice. That puts enough pressure on the ice to begin to melt it. And that's what makes it so slippery. That's what makes figure skating, hockey skating, possible. That doesn't happen with most things. Here, if you've got a solid and you put more pressure on it, it's just going to stay a solid. So here we've got iodine. That's 100 atmospheres. Here's 1 atmosphere. Where am I? I'm getting lost. This is the sublimation curve down here. And then this is for carbon dioxide. So here at 1 atmosphere, as you increase the temperature, you're just going to cause the carbon dioxide to sublimate. At 1 atmosphere of pressure, there is no temperature at which liquid CO2 exists. That's kind of crazy. Here for iodine, there is a range in here where the liquid would exist. But iodine also sublimates quite easily. So any question about phase diagrams?
Do we have questions on the test, like labeling it?
There could be questions that ask you to label it, yeah. They might give you, the bare bones of this diagram, but not have solid and liquid and gas labeled. They might ask you, which is the fusion curve, or, yeah.
So is the triple point where like the pressure is low enough to where it's boiling, but also like temperature is at the point where it's like freezing?
Yeah. Yeah. Yeah, so the triple point is where we have the solid, the liquid, and the gas all in equilibrium together, which is a bit mind-boggling if you think about it too hard, right? We don't see it happen because it's at a very particular pressure and temperature, right? And for a lot of substances, it's not something that you're going to run into. Like this one happens at 5 atmospheres of pressure.
Yeah, my question was, in the lab, are there certain substances that you're able to see the triple point easier?
I think probably T-butyl alcohol, the one in the video, is probably the easiest one. Yeah. Yeah, some of them are going to be super, super hard. Probably most things would be super hard. Yeah. Any other questions?